Leveraging our system, computations that used to take 12 hours can now be done in an hour. So there are a number of customers in a variety of different areas that are seeing positive ROI from leveraging our systems. Now, to be clear, this is not quantum supremacy. This is not even quantum advantage. What we are talking about is a customer benefit to leveraging our systems, a positive ROI over what they're doing today.
Skeptical about practical quantum computing applications? Perhaps DWave could change your mind. Over 100 real corporate customers are using their quantum annealing systems and software platform today in production. There are a lot of exciting advances to cover with their current machines and future roadmaps, but we also delve into what it really means to achieve quantum advantage, supremacy, and utility in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the CEO of DWave, Dr. Alan Baratz. Welcome to the show.
Thank you, Konstantinos. It's a pleasure to be here. Thanks for having me.
Yeah, DWave's been on before. We had Alex Condello come on to talk about like applications, and that's been a while. So I'd be shocked if our listeners haven't heard of DWave. It'd be pretty weird. But just in case some new listeners don't know, can you briefly tell us about the company and the types of machines that you're currently using?
Absolutely. So DWave is a leader in the development and delivery of quantum computers, software, and services. We are a full stack provider. So we provide everything from the hardware, the quantum computers, we design and manufacture them, to the quantum cloud service. Our quantum computers are available through our own cloud service, designed not just to support research experimentation, but to support business applications in production, through to our software development tools. We have a complete suite of software development tools for programming the quantum systems. They're source, so the developers can help us to enhance and extend, and then all the way up through to professional services, really focused on helping our customers to deploy applications. We are the first and only commercial quantum computing company. And by that, I mean that we're the only quantum computing companies that has customers that have actually sent applications into full production to help benefit their business operations. And you may be asking why. So just to kind of provide the context for that, at DWave, we selected a very different approach to quantum computing from everybody else in the industry. There are approaches. One is called gate and the other is called annealing. And we decided to start with annealing. And we did that because it's a much easier technology to work with. It's easier to scale, much less sensitive to noise and errors. And that's what has allowed us to get to the point where we can actually support business applications in production. Our cloud service is now available in over 42 countries around the world, and we are SOC 2 Type 2 compliant throughout our entire cloud service, all the way through to our quantum computers.
That's a great answer. That definitely captures it. We're going to dig into multiple points from that as we go through here. The first one for folks who might not be too clear on annealing gate-based, the high number of qubits in annealers, that often confuses people. You know, they talk about, oh, when will we get to thousands? And then all of a sudden they hear that you have thousands. It's like, what's happening? Was I hoodwinked, right? So could you explain that difference from gate-based systems and their lower counts and how that works?
Absolutely. So as I said a minute ago, the reason why we selected annealing is because it is a much easier technology to work with, much easier to scale. The reason for that is the qubits are simpler. Our qubits basically support spin up, spin down. And when they're in superposition, they are spin up, spin down at the same time. But they are not three-dimensional qubits able to support any position on the block sphere. That's them simpler to develop. That makes them more robust. And then the annealing architecture is much less sensitive to these and errors in its own right. And the reason for that is because when you perform a computation on an annealing quantum computer, if errors get introduced into the computation, you will simply settle into a solution. It may not be the optimal solution, but it will be a solution to the problem typically close to optimal. That's very different from a gate model system where once an error gets introduced into the computation, the system collapses into garbage. And you basically are left with nothing. So, annealing is easier to scale. That's why we're at a much higher qubit count than anybody else. It's less sensitive to noise and errors. And that's why we're able to deliver good, if not optimal solutions to hard problems today without the need for error correction.
Good enough counts in horseshoes, hand grenades, and annealing, I guess, basically is the idea. So you have these robust machines that have been around for a while and have already been used for some impressive things we'll get to. One interesting approach that you introduced a while back was hybrid. So this idea of having a powerful annealer and then some level of classical computation and then the two working together. So could you explain a little bit of how that works and maybe also touch on the newer nonlinear solver that's available?
Yep. So our quantum cloud service provides access to both the quantum computer natively as well as to hybrid solvers that bring together the quantum computer with classical CPUs and GPUs. And essentially, it's the hybrid solvers that allow us to solve problems larger than can be solved natively on the quantum computer. Now, our current generation quantum computers are very, very powerful. We've demonstrated some very significant performance benefits over classical on those systems, including a paper we published in Nature a little over a year ago, where we proved that our system performed something called coherent quantum annealing. So quantum annealing while in the coherent regime. And we're able to show that while we are performing coherent quantum annealing, we're able to get a polynomial speed up over classical on hard optimization problems. So the quantum computers themselves are quite powerful, but many real world problems, commercial problems, are larger than what can be solved natively today on the annealing quantum computer. And so to solve those problems, we use hybrid solvers. Essentially, the way the hybrid solvers work is they take the complete problem and start performing computations that essentially look for the hard subproblems embedded within those larger problems. And then the hard subproblems are sent to the annealing quantum computer for solution, and we perform a loop in that way. With our latest generation hybrid solver, we are able to support problems with up to 2 million variables and constraints. So we're talking about large, hard optimization problems where we're trying to essentially optimize some objective function subject to some very large number of real world constraints.
Yeah, that's a great answer. And is there an approximate percentage that seems to shake out? Like if you have to think of the whole problem as being done as like 100%, right? Is it like 80% is classical and then only the 20% is that really hard part? Like what would you say is the approximate?
So that's a very interesting question and not straightforward to answer.
I would expect it varies.
And let me explain why. So first of all, whenever you solve a problem, our system using a hybrid solver, we always report out how much time was spent on classical compute and how much time was spent on quantum compute. So you will always see those metrics whenever you submit a job to our hybrid solvers. However, you need to keep in mind that the quantum system runs much, much faster than the classical systems. So small amounts of time on the quantum system can represent far more powerful computation than large amounts of time on the classical system. But beyond that, there is a more fundamental reason why it's not straightforward to answer the question you asked. So a lot of times people think that a problem is either easy to solve or hard to solve. But it's not that straightforward. The hardness in a problem is actually not in the problem itself, it's in of the problem. Let me give you an example. Factoring numbers. Is that a hard problem? Well, people tend to think it's hard because it's the basis for our current crypto system. But actually, if I give you a random number and ask you to factor it, there's a very high probability that it will be very easy for you to factor. In fact, only a relatively small number of numbers are hard to factor, products of large primes. That's what key crypto systems are based on. So factoring in and of itself is a hard problem, but there are instances of factoring that are very hard. So when we go to solve a problem for one of our customers, it's not about whether the problem we're solving for them is hard. It's about whether the instance that they're submitting at a given point in time is hard or not. So one of the benefits of the hybrid solvers is that for the easy instances, classical is perfectly fine. But the quantum system is always in the loop. Every time you submit a problem to our hybrid solvers, the quantum system is always engaged and always performing a part of the computation. It's there as the backstop to ensure that when you get hard instances, you're able to solve them as well.
Yeah, and that makes perfect sense. I figured there'd be a lot of variation. It's funny because I don't think I've ever met anyone who's used all their DWave time up because these machines are so fast.
No, it's interesting because when anybody can get free time on our system. Yeah. Just simply go to cloud.dwavesys.com and you can sign up for time on our cloud service. We'll give you a minute of, if open source the work that you're doing, you can renew that minute every month. So you might say, well, what good is a minute? Well, within a minute of time, you can run between 400 and 4,000 jobs on the quantum computer. So it's actually quite a bit of time.
Yeah, it really is. Yeah, I've always been impressed with that. And then there's those ways to have like higher minute counts, and some companies have 20 minutes, and that becomes like an impossible thing to match. You can never really reach it. So what kind of roadmap are we looking for at DWave? How will the annealers and hybrid systems evolve over the next few years? And for a little while now, I've been hearing the stirrings of gate-based might be joining the family, which seems to kind of like be alien to the whole like philosophy. So I'd love to kind of hear both sides, like what's coming.
So there's a lot of interesting technology and product work going on at DWave right now. So first of all, our current flagship product is called Advantage. That is a 5,000 qubit annealing quantum computer. We have 3 of them in production today in our quantum cloud service. We have 15 others in our lab in Vancouver, where our R&D Center of Excellence is located. But 3 of those quantum computers are in production in our cloud service today. We are now working on our next generation system. We call it Advantage 2. Advantage 2 will have over 7,000 qubits, but it's not just about the qubits. For us, it's always about qubits, connectivity, coherence, and energy scale. Let me talk about each of those. As I said, with Advantage 2, ultimately, we will have over 7,000 qubits, up from 5,000. But it will also have more connectivity. Our current Advantage processor has what's called degree 15 connectivity. Each qubit is connected to 15 others. With the Advantage system, we'll be connected to 20 others. So we're increasing qubit count, we're increasing connectivity. Next, we're increasing coherence time. With the Advantage 2 system, we will have a 2x increase in coherence without error mitigation. With error mitigation, we will have a 20 increase in coherence time. So coherence time is up. And then finally, energy scale. With Advantage 2, we have about a 40% increase in energy scale. So what do all these things mean? Well, increased qubits and connectivity means we can solve larger problems. Increased coherence time means we get to the solution faster. And increased energy scale means we can specify the problems with more precision so we can get better solutions to them. So larger and more complex problems, better solutions, solved faster with the Advantage 2 system. Excuse me, we're making great progress with Advantage 2. We have a 1,200 qubit prototype available today in our quantum cloud service. Anybody can use it to start getting ready for the full production system. And we've got 4,500 qubits that have been fabricated that we are calibrating in our lab today on our path to the ultimate qubit system. So good progress on Advantage 2. And as we look to Advantage 3, Advantage 4, and then Advantage 5, it'll always be qubits, connectivity, coherence, energy scale. Now, there's a lot more interesting and exciting work going on than just that. Next point. We recently announced what we call fast annealing. This is a change to how we control the annealing quantum computer so that we can run the annealing algorithm much faster than we had been running it previously. And the reason why this is important is because I referred to a Nature paper from a year and a half ago where that we've been able to show coherent quantum annealing, namely annealing while we're coherent. Well, in order to be able to remain coherent through the anneal process, we need to run the anneal process faster. And that's what we are now able to do. And we just opened up that capability, fast anneal, to all our customers. So you can now use that. The next thing is that we recently were actually able to show how we can integrate, I'll call it digital, but actually it's gate model capability inside our annealing quantum computer. We've actually been able to show how we can manipulate the energy scale within the annealing quantum computer in addition to manipulating the spin of the qubits. What this means is that we can now read out not only in a second basis, but in arbitrary bases. Basically, more than spin up, spin down. This means that we'll be able to start combining some digital compute capability together with the annealing compute capability, all within the annealing quantum computer. And that's very exciting. Okay, now all of that having been said, we did also announce that we are working on a gate model quantum computer, a pure gate model quantum computer. The reason for that is that there are problems that require a gate model system. By the way, there are also problems that require an annealing system. So it used to be believed that a gate model system could solve all problems. Not true. A couple of years ago, it was shown both theoretically and experimentally that gate model computers will likely never be able to deliver a speed up on optimization problems, the thing that annealing computers are very good at. So we've got kind of a bifurcation in the application environment for quantum. Problems that will always require annealing, those are optimization problems. Problems that will always require gate, these fall in, for example, the area of quantum chemistry. But we have customers that have problems that require, think about a drug company that's working on drug discovery, developing a new drug, putting it through, manufacturing it. Some of the problems that need to be solved are quantum system. Some of them are optimization, like optimizing the trials and the manufacturing process requires an annealing system. So by having both an annealing and a gate system, we'll be the only company in the world that can solve the full set of use cases for our customers. And finally, many of the technologies that we had to develop for our annealing quantum computer can be directly applied to a scaled, error-corrected gate model system. So while we started working on the gate model system later than everybody else that's working on gate model systems, we actually think we've got a head start in some key technology areas for gate.
So is it going to be then similar? It's going to be semiconductor based, right?
So it will be semiconductor superconducting based. And in fact, if you were to look at almost all of the superconducting gate model companies and products that are in development today, they all use what's called transmon qubits, which are voltage-controlled qubits. Well, our annealing quantum computer uses flux-based qubits. They're controlled by magnetic flux. So our gate model system will also use flux-based qubits, which will also make us quite unique with respect to gate model. We've got a lot of experience with flux-based qubits. We understand how to fabric. They're actually easier to control. They've got some real advantages over trans. So we're quite excited about that.
Yeah, when you said you're using similar technology, I was like, well, I'm not going to say transmon then because it's not going to be transmon. Yeah. Okay. No, that was very clear. I think it's easy for people to visualize that. And again, to get that earlier sense of what you said, that when you're solving an annealing problem, you have to have these things stay alive and stay coherent and be able to get as close to the optimal answer as possible. So that's a really good point to make with this progress. We keep talking about like the customers of these machines and how you've had more customers that are real for quite a while. And the phrase that comes up is customer advantage. You guys created that. I love that phrase. I do. I'm a big fan because it's all practical implications. I always say that like if you're going to buy a stereo, you're not going to like hire a lab to benchmark every speaker on the planet, every amplifier on the planet. You're going to look for what kind of real world use you can get from leading options. So can you share what customer advantage means to DWave and give some recent examples from real customers, how they're using it in production?
Absolutely. Customer advantage simply means that there's a positive ROI for the customer in using our products and services. This could be better solutions. It could be faster solutions. It could be lower cost solutions. And typically it's measured against what they're doing today. Okay. Mm-hmm. So if we can come in and show them that we can deliver better solutions than they're getting today and at the same or lower cost, that's a positive ROI for them, right? And that's all that matters when, you're trying to help a customer improve their business operations. So that's what we mean by customer advantage. We have a number of customers. In fact, I think at the end of Q1 that we have over 120 customers. North of 65% are commercial. The other research and education. But we have a large number of commercial customers. For example, Pattison Food Group, which is a Canadian grocery chain, currently has 2 applications in production. They use it on a daily basis to run their business operations that access our quantum cloud service in support of those applications. One of them is an e-commerce grocery delivery application, and the other is an employee scheduling application. And a significant ROI on both of those applications. Another customer, very different space, is Vinci Energies, a large construction company in Europe. Vinci Energies has developed with us an Asian HVAC installation. So basically, this is the problem of routing the venting and the exchangers so that A, you have an aesthetically pleasing routing, B, you have a low routing, and C, you're achieving all of the ventilation requirements that are required. And leveraging our quantum systems, they've actually been able to show that they can develop routing and designs for these installations that are superior to anything that they're developing with their existing systems. And the solutions are computed much, much faster than the computation with their existing systems. Another example is Interpublic Group, a large ad agency that has basically worked with us on an application for promotional tour routing. So, when you want to create a promotional tour, there are all kinds of requirements and constraints as to with, where you're going to go, how you're going to get there, how you're going to pack the trucks, who are the drivers, what are the requirements on when they can drive, when they can't drive, and so on. Leveraging our system, computations that used to take 12 hours can now be done in an hour. So again, there are a number of customers in a variety of different areas that are seeing a positive ROI from leveraging our systems. Now, to be clear, this is not quantum supremacy. This is not even quantum advantage. What we are talking about is a customer benefit to leveraging our systems, a positive ROI over what they're doing today.
Yeah, they took a look at what their numbers were. They got maybe a 2% increase, spending whatever amount less, and that's instant benefit. Yeah,
exactly.
Yeah, that's and it's great. Thanks for those examples, because they were not the examples I'm sure most listeners were expecting. They were expecting to hear big bank name, big oil company. That's what they were expecting, right? They were expecting something like that. And it's kind of amazing that businesses of all sizes can come up with these use cases and execute a workload, basically. Just like any other cloud workload. Yeah, it's terrific.
Exactly.
And speaking of big, are there any U.S. government use cases for DWave currently underway?
There are. So we are working with a partner, Davidson Technologies, government contractor, particularly in the areas of space and missile defense. And they've looked at a number of different applications. So they've worked with us on an application essentially for scheduling how radars communicate with moving objects in space. And they've been able to see that leveraging our systems, they can get about a 15% increase in utilization of the phased array radar systems. They also worked with us on a missile defense station. So you've got incoming threats and you've got countermeasures, and you've got to figure out which countermeasures to apply to which threats to best neutralize. Leveraging our system, they were able to evaluate more than 65 million possible solutions in about 13 seconds. So there are some interesting use cases across many, many different industries, including government. By the way, since I mentioned Davidson, we did also recently announce that we are going to add a fourth system to our cloud service, and it will be located at Davidson's new headquarter facilities in Huntsville, Alabama. And ultimately, that system will be moved into a secure environment for supporting sensitive applications.
Oh,
so
wow.
We're pretty excited about that.
That is pretty cool. There's so few quantum computers really being implemented in an infrastructure like that without just pure cloud. That's pretty impressive. I had just read Annie Jacobson's book on nuclear war, and it scared me so much that I like the idea of coming up with more optimal countermeasures for things in the future, for sure. So I've publicly stated numerous times that the first benchmarkable quantum advantage will probably come from annealing, and probably an optimization use case, obviously, right? And as a result, most likely from DWave. So I know it's still in peer review, But can you talk a little bit about that infamous paper? I know you mentioned another one, but right now I'm talking about the recent one called Computational Supremacy and Quantum Simulation. It looks really promising, and just wanted to have your thoughts on that while it's still going through the process.
Yeah, we're excited about the work. We do believe that this is the first demonstration of quantum supremacy on an important maybe the first demonstration of quantum supremacy, but for sure the first on an important real world problem. So let me first spend a minute on definitions, okay? Because I'm actually quite concerned about the fact that the industry has been very self-serving in defining some important terms. Terms I want to talk about are quantum supremacy, quantum advantage, and quantum utility. So John Preskill, Caltech, originally defined quantum supremacy. And the definition was very simple. This was a quantum computer solving a problem that cannot be feasibly solved classically. Very straightforward. Okay. Now, subsequent to that, the industry came up with the term quantum advantage. Now, there are some that would like to say that quantum advantage is the same as quantum supremacy, but it isn't. It's different in two important ways. One is that quantum advantage typically refers to illustration on a real world problem, not a contrived problem. Okay. Second is that advantage spans the gamut from better than classic to cannot be solved classically. Okay, so supremacy was clear, cannot be solved classically, didn't matter whether it was contrived or real world. Advantage, typically real world, but spans from better than classical to can't be solved classically. Unfortunately, different companies have taken advantage and defined it in different ways. And so it's become quite muddy. But in my view, it should be very simple. Quantum advantage is solving a real world problem, not a control, better than it can be solved classically. Whereas better could be just a little better all the way up to a lot better. Okay. Then there's quantum utility. Now, the industry has really screwed up quantum utility. Mostly IBM has screwed up quantum utility. Basically, what they did was they put out a result and said, this is quantum utility. When it was shown that the result wasn't quite as strong as they thought, they redefined quantum utility so that the result was still quantum utility, right? By saying quantum utility is essentially solving a problem better than it could be solved by brute force classical. Well, that's ridiculous because nobody uses brute force. Everybody is always using heuristics to try to come up with better solutions. But my view is quantum rightfully should be real world problem and not be solved classically. Okay, so if you think about what I've just said, think about a 4-quadrant chart, right? Where basically the left side is contrived, the right side is real world. The bottom is better than classical, the top can't be solved by classical, okay? Supremacy, up 2 quadrants. Advantage is the right 2 quadrants, and utility is the top right. It is the most substantial. It is a real-world problem that cannot be solved classically. We think that's what we've demonstrated in the archive paper that we posted a few months ago and is going through peer review now. It is the ultimate real-world problem that can't be solved classically. I'm excited by that. And I'd love to talk more about it, but let's wait until it gets published.
Yeah, it looks promising. I know there has to be some extrapolation in it. For example, you're not really going to run the Oak Ridge machine for 1,000 years or whatever. But yeah, from what I read and the digging I did, it looks pretty awesome. So I can't wait to see the peer review process play out. And I've talked a lot about the peer review process on here and how important it is. But those quadrants you described were like a really good way to understand it. So as we're starting to wind down here, a couple other questions. So machine learning, like binary classification, et cetera, it's been a major category of quantum computing for a while now, use cases. Since then, generative AI has grabbed a lot of attention, to put it mildly. Can you talk about where the industry is going with AI and quantum, in your opinion, in general?
So we think there's a lot of synergy between AI and quantum. For me, there are three areas in which quantum and AI come together. The first is simply the two are synergistic, and there are problems that require both. Imagine for a minute using generative AI to predict demand for products next year, and then using quantum optimization to optimize the supply chain to support that demand. Okay? Now that's an example of generative AI and quantum optimization working hand in hand to solve a problem. Second, I believe by leveraging quantum distributions, we will be able to train AI models that are more accurate. And the reason is quantum distributions have more degrees of freedom than classical distributions. And so you should be able to get a better fit to the model, a more accurate model. And finally, there's some evidence that quantum will be able to train models with much lower power consumption. And this is critical because, the GPU infrastructure is consuming massive amounts of power. We actually did some work in this area on a different problem class, not AI, a number of years ago, where we showed several orders of magnitude lower power consumption and solving problems leveraging our system than being a GPU farm. This comes back again in the Supremacy paper, which I'm not going to say too much about. But if you go look at the paper in the archive, you'll see that we talk about both the ability to solve the problem and the amount of power consumed. So it's time to solve the problem and power consumed. And I think that this will apply to model training as well, as we're already seeing some early results in this area. So whether it's quantum and AI working together to solve problems, or quantum helping us to build better models or helping us to build models with lower power consumption, I think all of these represent areas where we'll start to see quantum and AI come together.
Yeah, and I'm going to link to that paper in the show notes because it's something everyone really should take a look at. So before I let you go, can you remind listeners of the different ways they can access DWave systems and basically what the benefits to each, right? Because certain platforms give you certain capabilities.
Yeah. The only way you can access the computer is through our quantum cloud service. It's called Leap. And as I said, you can get to it by going to cloud.dwavesys.com or leap.dwavesys.com. You can sign up there and you can get free access. If you want to buy time, we'd be more than happy to sell it to you as well. Once you are in the Leap cloud service, you get access to all of the quantum computers that are in the service. There are 3 of them in production today, plus the 1200 qubit Advantage 2 prototype system. So you can access all 3 of those systems. You can access them natively, or you can access them through our hybrid solvers. And today we have several hybrid solvers in the cloud service as well, including our newest generation non-linear hybrid solver. And all of these capabilities are available to all of our customers. Finally, we have over 50 applets in Leap that can give you a quick start to building your application.
Yeah, and it's those templates that kind of let you visualize why different size businesses are able to use this environment, right? Yeah,
exactly.
It's worth noting. So thank you so much. I really appreciate you taking the time. And these were some incredibly clear answers. So I'm sure our listeners will enjoy that. Thank you.
Thank you. It was a great pleasure. I appreciate the time.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at time. Let's recap. DWave is a commercial quantum computing company. Its annealing systems and cloud platform are used by over 100 customers worldwide in production applications. Unlike benchmark claims of advantage, these use cases yield performance improvements and cost savings over classical solutions, and that's compelling for sure. DWave is focused on magnetic flux-based qubits that use a superposition of two states, unlike the multidimensional block sphere of a gate-based qubit. However, these qubits are high fidelity, and when thousands of them are put together in an annealing system, impressive results are obtained in optimization use cases. DWave expects to take its Advantage system from 5,000 to 7,000 qubits when Advantage 2 comes out, and each qubit will be connected to 20 others, up from 15. Future plans include a digital mode that runs gate operations with these machines and an actual gate-based quantum computer using flux qubits. Some problems work well with a hybrid combination of classical and quantum. DWave has hybrid solvers available in its Leap platform that allow you to submit a job and have the system determine which parts are best handled by quantum or classical. You get a breakdown of what happened after, including time spent on each type of system. A recent paper, in the show notes, generated a lot of buzz in the industry with its claims of quantum supremacy and probably utility if you consider the definition and what was done. Alan explained these definitions perfectly. Quantum advantage is when a system can outperform classical in either a contrived or real-world use case. Quantum supremacy is when a system can do something contrived that a classical machine could never do. And quantum utility is when a system can do something useful in the real world that a classical computer could never do. Read the paper, which is currently in peer review, and weigh in. With entities ranging from supermarkets to government weapon systems using DWave systems, the company rightly believes we're already in the post-quantum world. Sorry, couldn't resist. That does it for this episode. Thanks to Alan Baratz for joining to discuss DWave, and thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.